GM everybody, my name is Nino and I'm a Web3 developer at Soulbound Development Agency, and also I'm a member of a local Solana community called Super Team Balkans. My main field of work is based on the Solana ecosystem, precisely building Web3 gaming products like the Heist, the most played idle game on Solana, blockchain tooling and custom smart contracts written in Rust on Solana virtual machine for our clients. Initially, I started my career as a Web2 developer and got interested in blockchain technology and the whole idea of decentralized internet around mid-2022 or late 2022, which was an especially interesting period because that was the start of a devastating bear market, and everybody who was building on Solana during that time knows how hard it was to be taken seriously. But here we are now, everything is better than ever, and we know that all the hard work we put in during the bear market really paid off. The topic of my talk is Solana State Compression, theory behind it, and the use case of building cNft or compressed NFT standard. Solana State Compression is a technology which allows teams to build large-scale Web3 experiences at zero to low cost. It became popular and gained its initial hype around April 2023, when teams were able to mint insane amounts of compressed NFTs and distribute them, which was unseen in the blockchain technology until that point in time. Every other blockchain technology can also implement its own state compression technology, and all of the blockchains really implement it in a way that they hash all the transactions together to produce a single block hash. But the main difference between Solana and other blockchains is Solana's community and Solana's ecosystem, which utilizes technology in a way that was unseen before and at scale that didn't exist before. This technology is also one of the main reasons why only possible on Solana phrase caught traction, because it's really, some products are really only possible on Solana. Before I start explaining how state compression technology works, let me introduce you to two types of memory on the Solana protocol. The first one, ledger space, and the second one, account state. Ledger space is your standard list of entries containing transactions which are signed by clients. Every blockchain has some sort of ledger space because every blockchain needs to store all the transactions and logs they produce until the genesis block. The second one, account state, is a record in the Solana ledger that either holds data or is an executable program. So that is part of the memory which either holds some arbitrary data or acts as a smart contract. The best way to understand account state is to understand three different types of account state. The first type, wallet, which exists on any other blockchain, is a standard data type which stores Lamport balance data and has its associated secret or private key. So it's literally a key pair of public key and secret key. The next one, PDA or program derived address, it mainly stores program or smart contract data or state and doesn't have its associated secret key. Programs are by nature on Solana protocol stateless, so we need another structure which we can use to store their state. The way we do it is that we generate a public key of a PDA or program derived address in a way that we use program ID or smart contract public key, combine it with some seed, which is an arbitrary data. We choose to point to that specific data entry in account state and run it through a function in a way that we find the first public key which doesn't lie on the elliptical curve, which means that that public key doesn't have its associated secret key and that it's impossible to change or update data on that account without running it through the smart contract instructions. And the third type of account state is a program account state. It mainly points to the binary code which represents smart contract and its update authority. Smart contracts on Solana can be upgraded at any time if it's set in a way that it's upgradable, and upgrade authority is just a wallet which has authority over upgrading that smart contract. There are some pros and cons of using both ledger state and an account state, and I'm going to run through all of them. The first pro of using ledger state is that it's very cheap to store data. The reason why it's very cheap to store data on ledger state is because we don't need to validate all the previous and old data to insert the new transaction inside the new block. And every entry can be tracked down to the Genesis block, which means we have the complete changelog of all data on the blockchain since it was first released into the production. The two main cons of using ledger state is that it's really hard to access data, and we need to make some custom indexing services or solutions, or even store data off-chain in some sort of caching system. Reason why we need to do that, because ledger state is literally terabytes and terabytes of data, and if we need to pinpoint the exact data entry we need to use, it's really hard. So we need to implement some sort of custom indexing solution or store the data off-chain, exact data we need, in a database like SQL, MongoDB, or Redis. And the second con is that it's not directly readable nor editable by smart contracts. So if we want to edit or read data from ledger space inside smart contracts, we can't do that. Now let's take a look at pros and cons of using an account state. The first pro of using an account state is that it's easily accessible. Each RPC has its own implementation, standard implementation of indexing all the data on the account state, and we can easily and in a fast way access that data. And all of the data on account state is directly readable and editable by smart contracts. So if we need to do some changes to the data, we can do that. The only con of using an account state for storing data is that it can get relatively expensive for storing big amounts of data on the blockchain. So let's take, for example, 1 megabyte of data. If we want to store 1 megabyte of data to an account state, we need to pay upfront 6.96 SOL, which would be maybe $1,000 and a few $100. That price is refundable, but only when we don't need access to that data anymore, or if we want to remove that data from the blockchain. State compression solves this problem. It is a method of creating a fingerprint or a final hash of off-chain data and storing this fingerprint on-chain for secure verification. So we take all of the data entries we have and want to store on-chain, hash them together, and store only the final hash we get from those operations on-chain. So that's literally storing only 32 bytes on-chain instead of storing megabytes and megabytes of data. How state compression works? It works in a way that we get all the hashed data entries and store them inside a ledger state through transaction logs. We produce the final 32-byte hash value by using Merkle tree data structure and store it inside the account state, so on-chain. And if we want to verify that some data entry is included inside a Merkle tree or some data entry is included in that 32-byte hash value, we can do that by using Merkle proof, also known as membership proof. I'm going to talk about it a bit later in a visual example. Here you can see a visual example of a Merkle tree that has 8 data entries. It doesn't need to have the 8 data entries. It can have any number of data entries, which is to the power of 2. But for this specific example, I used 8. We take each data entry. For example, I want to build an app that stores nodes on-chain. Each node would be each of these data entries. And if you use non-similar types of data as data entries, that would be considered an anti-pattern. It's possible, but not recommended. So let's say each of these data entries is a node. We hash each of the nodes and produce what's called leaves of the Merkle tree. So leaves are hashed data entries. Then we take all of the leaves we got, hash them together to get hashed nodes called branches. We hash all of the leaves in a way that we take the first two leaves, the second two leaves, third two leaves. So we take a leaf at index 0, leaf at index 1, hash them together, produce a branch at index 0 and level 1. Then hash leaves at index 2 and index 3, index 4 and index 5, etc. Once we produce enough or all of the branch nodes, we then repeat the process until we get to the final hash, which is called the root hash. If we want to confirm that one of these data pieces or data entries is actually included inside a Merkle tree, we can do that by creating a Merkle proof. We do that by taking a data entry we want to verify. Let's say I want to verify a data entry at index 0. Then I take the first sibling hash and hash them together to create the first branch node. I take the first branch node and the first sibling of that branch node, hash them together to produce another hash node, and repeat the same process until I get the root hash. Then when I have the root hash, I compare the root hash I calculated with the root hash that is stored on chain. If it matches up, then it means that the data I tried to check is actually a member of this Merkle tree. But there is a problem with using standard Merkle trees for compression on Solana, and that problem is that we can't do multiple updates inside a single block. So let's say 5 users tries to update data entries at the same time and get included in the same block. Only one of those updates will pass, because the first update which passes will invalidate and change the root hash, which means that once we try to validate other changes, it will fail because we will have the old root hash and we can't compare it anymore. So concurrent Merkle trees solve this problem. They are a special type of Merkle tree which enables multiple updates inside the same block by storing some sort of changelog on chain. Changelog is literally a struct instance in Rust, which defines some data points which represent data changes. So we produce multiple changelogs and batch them together inside a single update. So we don't have invalidation problems anymore. There are 3 parameters we need to consider when creating concurrent Merkle trees, and they are max depth, max buffer size, and canopy depth. Those 3 parameters are defining the final cost of storing data using a Merkle tree. Max depth is a maximum number of hops to get from any data leaf to the root of the tree. So it's basically number of levels minus the root hash level of the Merkle tree. Next one is max buffer size. It is a maximum number of changes that can occur on a tree with the root hash still being valid. So it's a number of updates we can do in a single block, or number of changelogs we store on chain. And the third one is canopy depth, which is a main factor in increasing the size or cost of storing data on chain. And it is a number of proof nodes that are cached on chain for any given proof path. That means that if I have max depth, let's say, of 20, we have 20 levels of a Merkle tree. And if we want to prove membership of one data entry inside that Merkle tree, we would need to pass 20 32-byte values inside the transaction to validate it. But the problem is that max transaction size on Solana is around 1,232 bytes, and it's really easy to exceed it by passing all the proof nodes through the transaction. So we solve that in a way that we store some of the proof nodes or sum of the branch levels on chain, so we don't need to pass them as instruction data. And in that way, we won't exceed the transaction limit. Here we have a visual example of a concurrent Merkle tree. This particular concurrent Merkle tree has a max depth of 3, and if we calculate 2 to the power of n or 2 to the power of 3, we get the number of leaf nodes or number of data entries that can be stored inside this Merkle tree. And we can see that it is needed 3 hops to get from each data leaf to the root of the tree. Next parameter is max buffer size. I set it to 8, and it represents 8 on-chain changelog entries. So on the right, you can see how each changelog entry looks. It's a small piece of data. It isn't the main factor in determining price of a tree, because if we have 8 max buffer size, it will increase the size of the data we store on chain by only a few hundred of bytes. And the third main factor in deducing the price of storing data on chain is the canopy depth. In this example, I set the canopy depth to 1, which means that I stored only 1 level of branch nodes on chain, and it is the upper level of branch nodes. And if we run this number through the formula 2 to the power of n plus 1 or 2 to the power of n of 1 plus 1, we get 4 nodes. There's a small typo here on the presentation. I didn't subtract this number by 1, so I get the number 4 instead of number 3 of on-chain stored hashes. If you want to know how much it would cost to store data on-chain, you can look at the official Solana documentation, which says that if we want to store 1 million entries of data with a Merkle tree of max depth of 20 and the canopy depth of 15, so we store 15 levels of nodes on chain, it would cost around 15.8 Sol, or maybe around $20,000 for storing 1 million data entries on chain, which is pretty cheap. One of the main use cases of Solana State Compression technology are cNFTs or compressed NFTs. cNFTs are an NFT standard built upon Solana State Compression technology, where each of the leaves of a Merkle tree actually represents one NFT or one NFT metadata. cNFT data can be indexed and accessed by using Metaplex DAS or Digital Asset Standard API, which is implemented by most of the RPC providers like Helios, like Syndica. If you want to know how much would it cost to store huge amounts of NFTs using cNFT standard, you can look at this table. So if you want to store 100 million cNFTs on chain, you would need to pay around 56 Sol to do that, where most of the price would be from transaction fees and not from data storage. cNFTs also had a huge impact on the whole NFT scene, especially on Solana. Here you can see a graph which indicates number of NFT mints per week. You can see that until April 2023, when the cNFTs began to use extensively, we had around 2 to 3 million mints per week. But once cNFT standard came, we increased that number to 30 million, 40 million. We literally 10x'd NFT production by using this technology. And one of the best examples of product using Solana State Compression and cNFT technology is definitely Drip House. I'm not in any way associated with them, but I support their work. And the main thing I wanted to highlight about them, they allowed regular users which don't want to pay any money to get free NFTs by subscribing to different artists and different creators. And in a year and a half of their existence, they managed to mint and distribute 100 million of NFTs, which is an insane number for a single product on a single blockchain. If you want to learn more about Solana State Compression technology, you can follow these links I have on the presentation. So you can go to Solana official documentation, SolDev course, Helios blog on cNFTs, and Metaplex documentation on cNFTs. That would be all. Thank you for your attention. If you have any questions, we have 6 more minutes for them. And you can see all of my contact info if you want to talk about Solana technology. Thank you.
So hi, Nino. Great
Hi.
presentation. Just a quick question. So if I want to employ cNFTs today, do I have access to some kind of library for that? Or do I just follow whatever is available on the links you posted?
Yeah, you have access to the Metaplex library and the Bubblegum program, which makes it easy for you to create cNFTs. But if you want to do some custom solutions with Merkle trees, you can use the standard Solana program library state account compression program.
Okay, so there is an account compression program. Thank you.
Yeah, thank you. Thank you, everyone.